right, so we're continuing the Research and Creative Works live presentations with computer-generated Mega Man levels with Benjamin Capps.
Great. Hi, my name is Benjamin Capps, and I'm a computer science and mathematics double major here at Southwestern University. And over the summer of 2020, I did research on generating Mega Man levels using generative adversarial networks. So some motivation in previous work is that this procedural content generation via machine learning using generative adversarial networks has been proven to be effective in both Mario and Zelda. And that's stuff that Dr. Shrum and his peers and students have worked on in the past, as well as a few other games that Kirby had mentioned. So some special challenges for Mega Man when generating these levels is that unlike Mario, where it's like standard left to right traversal, where if you spawn right here, and it's your primary goal to traverse as far to the right as possible so you can end the level. Mega Man has a sort of snaking pattern with the segments insofar as you may spawn in this corner right here, but you may have to travel up and around in this weird snaking pattern, jumping up and climbing ladders and so on to try to traverse the level through enemies. And so so the traversability of the level really depends on the type of segment. So you can't traverse up a level if it's if you don't have ladders or some way to go up, right? So some Mega Man training, how we trained the GANs is that we took the original levels, and the video game level corpus contains data in a text-based format, as Kirby said, in how to what each tile represents. So these dashed lines are air tiles, the P is the player, and so on. And then we sort of slid the screen across the level, all the levels, and took each of those screens, and that was a single segment of training data. So from there, we used a generative adversarial network, which during training, it includes a generator and a discriminator. And so what happens is that, say a member of the original training set is fed into the discriminator, and the discriminator's job is to determine whether or not that is from the training set or generated by the GAN. And then based on the fact that it is part of the training set, the discriminator gets better at telling what real segments look like. And then a randomized latent vector is sent into the generator, and then it's passed through a convolutional neural network and outputs something that should look like a segment, but at first it will look nothing like a segment. And then the discriminator determines that it's fake, and then the generator gets better at generating fake segments. And this process repeats itself over and over again until the generator is so good at fooling the discriminator that the discriminator's opinion is no more than a guess. And so at the end of this training, we have a GAN that can produce a really convincing single segment. However, as I said earlier, Mega Man levels are a strip of segments that sort of snake along in a unique pattern. And so the traversability and beatability of the level and meaning of the level strongly depends on the structure of each individual segment. And so just because the generator is good at generating a single segment, that doesn't mean it's going to be cohesive with the rest of the level, right? So we use latent variable evolution. So originally this latent variable is randomized. If we tweak certain numbers of this latent vector, we can get a different kind of level. We can sort of tweak the elements of the level a bit. And so we use latent variable evolution to maximize the solution path length and the traversability of the level. So in other words, how long do you have to traverse before you can actually reach the end of the level, and how much of the level can you traverse, can you get to? So this is an excellent connection to biology, because we're simulating natural evolution insofar as the latent vectors that produce meaningful outputs can then reproduce and evolve to get better and better latent vectors that produce better and better segments that produce more significant levels. And so our baseline for this is a single generative adversarial network. So we took all of the data from every single one of the VGLC levels, and we compress it all into a single training set. So regardless of if it were a horizontal segment or a corner segment or a vertical segment, all of it was put into the same training segment. And the generative adversarial network was trained based off of everything. And so when we call the GAN, and it generates different segments that stitch along to be supposed to be a cohesive level, we find that it actually lacks a great deal of cohesion, and there's a lot of wasted space. And so the reason for this is that if you if you train on based off every kind of segment, then it gets confused as to what a segment should look like in any given space because it has no knowledge of what the segments around it look like. And so as a result, as you can see here, there are two entire segments that aren't used at all in this, this solution path. And there's a lot of sort of lack of cohesion and things just don't make sense, right? Like this ladder leads up to nowhere and like death, immediate death. And if you were to follow the logical progression of the level, you'd end up getting stuck in this bottom portion. So instead, our challenge was to find a way to generate these levels that still preserve the structure of any given segment at any given position. So in other words, how do we generate this segment to have a certain type of structure that's preserved? And so our approach is to use multiple generative adversarial networks. So in the original training data, we took any segment that is helping the player traverse down, and we put all of those segments into a single training set. We put all of the corner segments into each independent corner training set, and we put the horizontal and vertical levels, or segments, sorry, not levels, into each own individual training set. So in other words, at the end of the down GAN training segment, we could consistently produce a segment that has an opening on top and an opening on bottom and has some sort of platformability where you can sort of traverse down. Right? So it maintains the structure given any segment type as it's being called on. And so as a result, there are more sensible transitions, and it's sort of utilizes the space more. So as you can see, comparing to the single generative adversarial network, there's a ton of wasted space and two segments that are entirely unused, versus for this approach, all the segments are used and there's actually quite a bit of the solution path in each of them. So here is a map, here's a graph of all the solution path lengths from each generation across 30 different runs. And it has been found that the MultiGAN consistently produces levels that have approximately 50 steps more in the solution path length. And so in other words, MultiGAN levels create longer levels that you have to traverse in order to beat them. However, that's not the only thing that we're comparing based off of. So if we compare the novelty, so not just the solution path length and how long the level is, but how distinct each level is and how well each approach functions in generating distinct and unique levels, it was found that both the OneGAN and MultiGAN levels were better at creating diversity across levels than the original game, where OneGAN is slightly better. And in terms of how distinct the segments are, the OneGAN approach is better than the MultiGAN approach, having more distinct segments. In other words, MultiGAN repeats segments several times. Yeah. So the question is it better to have a longer solution path length and to maintain the structure of each individual segment, or is it better to have each segment be more novel, each level be more novel? And so as a result, we had to find a way to sort of qualify this and quantify it in some way. And so we had to find a way to play the levels to see if it is actually more fun to play a structured level or a unique level. So we messed around with converting the levels to a Mega Man Maker format. And so Mega Man Maker is a fan-created game. It's super easy to create and edit levels. It's got a huge range of enemies that we could sort of select from. And so as a result, we took all of our levels in this text-based image format and converted them into a playable format that we could then conduct a human subject study on to see how good each type of generation, each generation method is at generating levels. And so we found that the majority of participants thought that the OneGAN levels were harder. An overwhelming majority of participants thought that MultiGAN levels were more fun. And a majority of them thought that MultiGAN was more human-like, and it was sort of a coin toss in terms of more interesting. And so we'll talk about why the responses are the way they are in just a second. So the majority of participants, although not statistically significant, thought that the OneGAN levels were harder. And the reason for this is that the participants said that the OneGAN levels made no sense. They led to nowhere or the death screen. They seemed to be hard in a random and not really well thought out way. And it seemed to force the player to make a leap of faith at the start. And so looking at these comments and then looking at one of the OneGAN levels, it sort of makes sense as to why these participants thought that way, right? So there's this area where you can jump down, but it leads to nowhere. It's sort of death. And then as you're traversing through the level, you can only see one segment at a time, really. And so you just see this pit and you sort of have to jump down and hope that you're not going to land in spikes or fall to your death or land right on top of an enemy or something like that. So there's that leap of faith that they're talking about. And then if you were to traverse down here, you would see this water segment, but there's no way for you to get to it. And so it's sort of like, why is it there? It serves no purpose and you can't even explore it. And then down here, you could go into the water level, but what do? You get stuck. You immediately hit a wall. And so it's a little less sensical. So an overwhelming majority of participants thought the MultiGAN level was more fun because they knew what they were going to do and could make things deliberately harder for them in an intelligent way. And this is the MultiGAN. And the MultiGAN, there were many places they could go. And so unlike the OneGAN, where there are places you couldn't go, the MultiGAN levels were better at utilizing their space and allowing the player to traverse through the level completely. Okay, so MultiGAN levels were more human-like because they had repeated building elements, which is interesting because we were wondering whether or not the distinct segments were a bad thing, but the repeated building elements were found to be sort of a good thing. And as this is the participant's comment that was mentioned earlier, and it references this exact level. This is the level that they played that they're referencing when it said it was getting harder for them in an intelligent way. And that sort of makes sense, right? So here you're just doing a simple, you have to jump over the spikes and then you're traversing along peacefully. And then you start, running across more enemies and more difficult, like jumping puzzles. And so it becomes progressively harder, which is interesting. Okay. So that was the biggest finding here, is that the OneGAN levels were not as human-like because they spawn the player next to enemies. It's like impossible not to take damage from them. It was random and frustrating, and there were just random blocks sort of floating and not serving a purpose, whereas MultiGAN levels did not do that. Okay, so some special thanks to the Scope program, the donors that allowed this opportunity to exist for me, and special thanks to Dr. Shrum for helping me along the way and being a guide for how to do any of this. And so finally, if you want to look at any of these levels, play any of these levels, we put all of the ones we generated onto a website, and you can access that website through this link or scanning this QR code here. All right, thank you.
Yeah, virtual round of applause. This is a really cool presentation. Ooh. Are there any questions or comments for Ben? We have some time before our next presentation.
I'll just chime in. I have a quick question. So this was super interesting. One question I had when you were talking about the GANs not producing a traversable level or whatever, when you had just like any segment could happen. I was wondering, like, is it possible, and maybe this is just completely unrelated to what you guys were doing, but like, is it possible to pass information like state? Like the previous segment was a down segment, therefore, you know what I'm saying? Or is that like just basically what you did in the second version?
Yeah, so that is exactly what we did in the second version. Okay. So when we generated levels using the second, well, so we did it technically for both, but the difference is that with the single GAN, it doesn't know what to do with that information, right? So here we generated a segment, and then when generating this segment, we said the last segment generated was a horizontal segment, and OneGAN sort of took that and said, okay, whatever, I'm going to generate any random segment because that's all I know how to do. I only know how to generate one segment. And so when generating this, yes, we still told it you need to generate this type of segment, but it was bad at it.
Gotcha.
Right? Whereas in this one, we said, okay, previous segment was a down segment. So now you're going to generate a down segment. And so it does so really well because it says, okay, I know that last one is a down segment, so I'm going to generate a down segment. So it preserves this sort of structure. So excellent question. Thank you.
Then related to that is conditional GANs, because conditional GAN would take that information. So do you want to elaborate on that as well?
Yeah, so in this approach, we had several distinct trained GANs that we just called on one at a time. And so they're all sort of separated, but a conditional GAN takes all that information into account. And so it's a single generative adversarial network that we tell it, hey, I want to generate this kind of segment, and then it can generate that kind of segment for us. And so it's similar to this approach, but it's contained in a single GAN.
And maybe we'll do that in the future, but there are reasons why it didn't quite work out this time.
This is personally not part of my wheelhouse, but I really liked having both of these presentations kind of back to back to kind of, I like that they built upon each other. So that was great.
Can I ask another question? Okay, so so back on the same idea. Like obviously you're teaching it like which levels are, you know, good or bad, or, you know, they're getting ratings, it's learning, blah, blah, blah. Like, could you also teach it then like which level it should expect to do next? And so this is getting at the same question, I know, but I'm just saying, like, in addition to teaching it how to make a good segment, like, could you teach a conditional GAN, like when to make this kind of segment versus that kind of segment, as opposed to just telling it like, hey, I'm a down segment, you're making a down segment? Like, could it learn through an iterative process like the individual ones are learning?
Okay, so you're asking, so in our case, we told it they're going to generate a down segment. What you're asking is, could it figure that out somehow?
Yes.
Okay, theoretically, yes. But at the same time, sort of the question is, like, why would we want to do that? Like, yeah.
So I guess what I'm saying is, like, more, not necessarily practically, but like from a theoretical standpoint, like, it seems like really cool that you're using evolution and like this learning algorithm to make the segments make themselves better, essentially. And like, I'm just wondering if you can also incorporate that into the like creating of the map of the segments as well.
Yes, we could.
We can talk more about the details of that. It depends on which part you're wanting to have the incentive to learn versus which, you know, do you care just more about the end result, or do you care about which part generates what and how it does it?
Well, if there aren't any other questions or comments for Ben's presentation, again, round of applause. It's so cool to see these presentations from our students. And I'm going to do a little housekeeping on my end and get our next presentation started to go right at 1:40.